Hi, my name is Ivo and I'm doing open source research into Nikola Tesla's impulse electricity. In my previous two videos I showed you the power cycle of an electric resonant system and my intention to generate power by placing voltage impulses on the resonant current maximums. Now I will show you how to place these impulses anywhere on a resonant cycle. The circuit that I will use to show this is a solid-state Tesla oscillator that was first published in 1919. Let's take a look. Let me explain in short the working principle. It is based on repulsing magnets. When repulsing magnets are brought together, they will try to get away from each other. And the same can be done with resonant coils. When two fixating coils are repulsing, the magnetic field of one coil can be pushed sideways. And the amount of distance between the coils determines the phase shift of the resonant cycle. The impulses then are injected at a different time in the phase as the phase is being shifted. I will come back to this later in this video and explain it into more detail. I will show you how I can place the impulses anywhere on the resonant cycle by using a solid-state Tesla oscillator. This circuit was first published in the July 1919 Electrical Experimenter. I placed a link to the article in the video description below. I've made a solid-state version of the Tesla oscillator circuit, and this is it. I now will first explain the functions of its parts, starting with the three coils. All the three coils are bifilar Tesla pancake coils as he described in his 512340 patent. I have two videos about how to make them out of pure copper speaker wire and phi ratio. L1 is the impulse generation coil. L1 is pulsed on and off by the MOSFET that has a 50% duty cycle. L2 is series resonant with its tuning capacitor. The L2 series tuning capacitor can be placed on either side of the L2 coil as long as the capacitor is connected to the inside rim of the coil. L3 is tuned by a parallel capacitor. L3 is also grounded on its outside rim. So all the three coils are resonant on the inside rim, even the L1 coil, as the impulses are resonant half waves. How are the coils stacked? The L3 coil is in the middle and is close coupled to the L1 coil. The L2 coil is on the other side of L3 and is loose coupled to L3. Now let's take a look at the L2 series tuning capacitor placement. One leg of the series capacitor is always connected to the inside rim of L2. The total combination of the L2 coil and its series capacitor can be swapped around between the MOSFET drain and source. This swapping changes the phase of the series resonance of L2 with 180 degrees. In result, we can place the impulses in the first or second half of the resonant cycle of the series resonant L2 coil. When the capacitor is connected to the MOSFET drain, then all the three coils are wound in the same direction. But when the series capacitor is on the source side of the MOSFET, then we need to flip L1 over. Let me first explain the basic setup that you are seeing here. Here are the stack of pancake coils. There are 3 coils together here. The top 2 coils are close coupled together. The bottom one is distanced by this distance holder. The top coil is the L1 coil. The close coupled coil in the middle is L3. And L3 has a parallel tuning capacitor here. And the bottom coil, which is distanced, is the L2 series resonant coil, which has a series tuning capacitor. Right now, this tuning capacitor is connected to the drain of the MOSFET. This is the MOSFET switching board. I've got 2 MOSFETs in series, and they are simultaneously switched by a 50% duty cycle square wave pulse. And the source of the MOSFET is connected to the L1 coil and the L2 coil. Then the probes. I have got a current probe here. This is probing between the L3 coil and parallel tuning capacitor. So it's measuring the resonant current of the parallel resonance of L3. I've got another high voltage probe here measuring the voltage of L3. It's on the same point as the current probe. And here is a high voltage probe for the L2 series resonance. It is probing between the capacitor and the L2 coil in, so we can see the voltage there. And I've got another probe here, a high voltage probe, that is measuring the impulses created by L1 on the source. The voltage probe of L3 and the voltage probe of L1 will be swapped because I only have 4 channels on my scope. There will be only one connected at a time, and I will tell you which one it is. One more thing, the current probe has an arrow on it, and this arrow is pointing inwards to the inside rim of the L3 coil. I always probe the same way, pointing inwards to the inside rim of the coil. I've done several tests to see what the current polarity is on all the coils, and I learned from that the phase only shifts when L1 and L2 have opposing magnetic fields. So the phase of L2 is shifted by the opposing magnetic field of L1, and when they're close enough, when they're really close, it's 180 degrees shifted, but when they're a little bit close together, then it's 90 degrees shifted. So I can tune the impulse to the voltage minimum where the current is maximum. Let me explain this a little bit better with 2 magnets. I will flip one magnet over. So now they are opposing. And these opposing magnetic fields, you can feel them when you bring them together. They just don't want to get together. And if you push them closer when they're feeling each other, then you can not get them together. One will slip sideways. And the one that slips sideways is the weakest, that has the lowest impedance. And L2 also has a low impedance. So this is what happens between L1 and L2. L2 is series resonant, has low impedance, and is shifted sideways when it is brought closer to the L1 magnetic field. And at the right distance, it will only shift 90 degrees. And this way we can tune the impulses. This is the principle. First, I need to make clear that I use LMD resonance between L2 and L3. In this resonant mode, the voltage and current of L2 and L3 are 180 degrees out of phase. I explained LMD and TEM resonance in my radiant half-bridge circuit producing LMD and TEM resonance of November 2020. So I will not go into it right now. Now that we know how to place the impulses on either half of L2's resonant cycle, let's take a look at how we can fine-tune the position of these impulses on L2. I have tuned the distance of the coils with this placeholder. It's an acrylic plate with some wooden bolts that can change the distance between L2 and L3. And at this distance the impulse is tuned to the voltage minimum, so it is on the current maximum. To tune the impulses onto the current maximum, we will need to change the distance between L2 and L3. And this changes the amount of coupling between the coils. At the right distance, the impulses will be tuned to the current maximum of the series resonant L2 coil. I will show you this in the next experiment. The L2 tuning capacitor is on the drain of the MOSFETs. That's why you can't see the impulse on the L2 sine wave. Okay, the system is now turned on, and you can see in green the current of L3, in yellow the voltage of L2, and in orange the voltage of L3. In purple is the square wave that pulses the MOSFETs on and off. I will now show you the impulses on the orange trace. I'll remove the probe and put the other probe on that channel. And here you can see the impulses. Let me remove the other channels for clarity. So as you can see, the impulse now is being generated right after the MOSFETs are turned off. What is a problem is that ripple after the impulse. This part. So this is the impulse that I'm using, and here is a ripple effect, and I haven't been able to explain this. I don't fully understand why this is happening. Maybe it's a clue to what will be beneficial one day, but until now I don't understand this, so I will ignore it for now and focus on the impulse. Let me zoom in to the impulse so you can see the duration of the impulse. We now have 200 nanosecond per division horizontal, so the impulse is around 450 nanoseconds in duration. The voltage division is 100 volts per vertical division, so we now have 1, 2, 3, 4, 500 volt impulses. My power supply is 2 times 10 volts, is a total of 20 volts because I use the channels in series to get really high voltages if I need them. And the amperage is 0.33 amps, which is rather low. As you can see now, I have tuned the impulse to the L2 voltage minimum. At that point, the L3 current is maximum. It looks like the L3 current is not maximum at the impulse, but actually it is a little bit amplified by the impulse. Furthermore, the current probe has a small phase shift. I'm now working at 80.5 kilocycles per second, and the phase shift of the current probe at 80 kilocycles is around minus 10 degrees. So the impulse is actually at the current maximum. The coils now are at a distance of around 17 millimeters. Let me now tune up and down in frequency with steps of 100 cycles per second, so you can see that I'm actually at the maximum of the resonant cycle. Take a look at green and yellow. You can see they are phase shifting, and you can see the maximum is right where that impulse hits the 0 point of the voltage. So this is very delicately tuned. Let me show you the impulse voltage also in orange when I detune. It becomes larger when I tune down, and at the 0 point it is minimum, and it becomes larger when I tune up. So the impulse is becoming smaller in voltage, in negative voltage. And for me, this is an indication that it is doing work. It is pushing or it is pulling. And at the same time, you can see the current of L3 in green is being amplified. There's a little bump on it. Okay. So right there, it is perfect. Here again is the phase relationship between the red voltage of L2, the blue current of L2, and the power cycle that it generates, whereby the negative cycle is a power generation and a positive green power is a power consummation. So by placing the impulse here on the voltage minimum of L2 in red, we can combine it with the current maximum, positive current maximum, and we'll have a power moment at the start of the negative power, where the power is being generated by the coil. To explain a little bit more about the generation of power, which is negative, or the consumption of power, which is positive, we need to understand that the electric energy of the series resonant system of the L2 coil and the L2 capacitor is exchanging energy between the capacitor and the coil. And I'm measuring the current between the capacitor and the coil. So when the coil is generating negative power, then the capacitor is being charged up. And when the capacitor is being discharged, then the coil is being charged up. It is consuming power, so then we have a positive cycle. So here the capacitor is charged up, and we can see that as the voltage is being increased. And here in the positive power cycle, the power is consumed and the coil is being charged up, as we can see that the current is being charged. And again, here the current is discharging, the capacitor is being charged to its negative maximum, so we have a negative power cycle. So each time the coil is charging up the capacitor, we have a negative power cycle, and that is where we increase the power to charge up that capacitor by placing the impulse there. I now have shown you how to place the impulses of L1 onto the first or second half of the series resonant wave of the L2 coil by changing where the series tuning capacitor of L2 is connected to the MOSFET switched. I also explained that L1 needs to be flipped over when L2 series tuning capacitor is connected to the MOSFET source. After that, I have shown you the impulses then can be fine-tuned to the current maximum by changing the distance between L2 and L3. The coil stack has parallel resonant L3 in the middle, close coupled to L1, while L3 is loose coupled to series resonant L2. L2 and L3 are LMD resonant, whereby they are 180 degrees out of phase. The circuit that I used is a solid-state Tesla oscillator. I will now continue to experiment with this setup to see if there really is power being generated by the impulses. There are several options that I want to try out. If you have any questions, let me know in the comment section below. All this information is open sourced. No patents can be applied. If you want to fund my research, you can leave a donation in my PayPal account. And I also added a Litecoin cryptocurrency address, which both can be found in my video description for donations. That's it for now. Thank you for watching and see you next time.